we stopped last time, and then we move on to a new chapter. It's about like signal analysis. But we stopped last time. Do you have any question before we start? Do you have any question before you start? Okay.
Not at the moment. No, sir.
Okay. So we just stopped last time that we can find the energy of the signal. Assume having a signal. This is my f of t. Okay. And this is t, and we need to find out what is the energy of this signal. So one way to do the energy of this signal is E of f. Would you please, did you see my writing? Integral from minus infinity to infinity, f of t square dt. Can you see my writing or no?
Yes.
Okay. Okay.
Yeah, we see that.
Yeah, I think the board is better than writing on the paper, right? It's better than before? Okay. So
It is way better.
okay, very good. So if we know what is the function of the signal, simply we just substitute, we do the integral from minus infinity to infinity, ft square dt. So then we can find out the energy of the signal. Another way to find the energy of the signal is using the frequency domain, which is energy is equal 1 over 2 pi integral from minus infinity to infinity, f of omega magnitude square d omega. So this formula, I can use this formula to find the energy in the frequency domain. Okay, so normally sometimes it's easy to find the energy using the time domain if we know the function f of t, but one of the important use for finding energy frequency domain is to find the bandwidth. Okay, so as we said here, if I need to find out, assume this is my the frequency domain of my signal. Okay, this is my f of omega, and I need to find out how much bandwidth is required to send this signal. Okay, so mainly if I need to consider to sending the whole signal, I need an infinite bandwidth. Okay, so from minus infinity to infinity. Why? Because f of omega is defined from minus infinity to infinity. But in reality, I don't need to, in order to send the signal, I don't need to collect all the energy from this signal. So the good thing about it here that like 95%. Yes.
Would you please click the record button?
Okay.
Thank you.
Thank you. So mainly we just need 95% of the energy. So 95% of energy is going to occur within this region. Okay. So in order to find the bandwidth required to send the signal, mainly we need to find out what? We need to find out omega 1 minus omega 1 to omega 1 here. Okay. So I don't require to find out what is to use the infinite bandwidth, right? Because the energy here on the tail is very small. So 95% of the energy will be what? Will be enough. Okay. So that's like one of the things here. So if I know f of omega, so then I know the energy of the signal, so then I can find out what will be the essential bandwidth to send the signal. So in most of the cases, sometimes I need also the time domain to find the energy. So I find the energy using the time domain, and I'm using this energy on the frequency domain formula, the Parseval theorem. So then I can find out what will be the essential bandwidth in this case. Okay, so we can modify the energy in this case to find the bandwidth 1 over 2 pi integral from omega 1 to omega 2, or since we're talking here about symmetric signal, we can say from minus omega 1 to omega 2, f of omega magnitude square d omega. So if I know what is f of omega square, I know what is the energy, I can find out what will be the bandwidth. I can find out what will be the bandwidth. Okay, so if I know what will be the is it okay now? If I know what is the frequency domain of the signal, I know the energy.
Good.
Then I can find out what is the bandwidth, which is by finding omega 1 and omega 2. So the only unknown here is omega 1 and omega 2. So finding the energy and the frequency domain of the signal, we can find out what is omega 1 and omega 2. Okay. So here is an example here. Calculate the total energy absorbed
Dr.
by.
Simon,
Yes.
I apologize, but it's not clear from the drawing what omega 2 is. Can you explain that?
Omega 2, just assume we're not having like, I would say, the signal is not symmetric, okay? So then we can find out omega 1 to omega 2. But if it's symmetric, we can just do from minus omega 1 to omega 1. Is this clear? Depend on the signal, depend on the spectrum of the signal, so we can decide. But normally, we know that the frequency domain of most of the signal is what? Is an even function. So then we consider only from minus omega 1 to omega 1. Is this clear?
Okay, so if I'm understanding this correctly, the minus omega 1 limits are for if it's symmetrical, but as a general case, we would need to do
Yes.
omega 1 and omega 2
That's true.
if we're dealing with any signal.
Yeah. But normally, we know from the when report to frequency domain that the magnitude of f of omega is always what? Always an even function. So if you consider like an even function signal, so then yeah, we can so omega minus omega 1 to omega 1. For generalized, can be omega 1 to omega 2. Okay, is it clear? Okay.
Yes, that's fine.
Okay, so let's do this example here. Assume calculate the total energy absorbed by what? 1 ohm resistors with an IT is equal 10 e minus 2 magnitude of t and the time domain, and then we can repeat the same thing for the frequency domain. So we're having a resistors, which is 1 ohm resistor, okay, and the current passing through this resistor is equal I of t is equal 10 e minus 2 t magnitude, okay? And we need to find out, this is the time domain, we need to find out what is the energy in time domain as well as in the frequency domain, okay? So to find the energy in time domain, we just use the formula, right? W, the energy, is equal integral from minus infinity to infinity, right? I square of t dt. This is the time domain, okay? Which is equal integral from minus infinity to infinity. I square is going to be what? 10 e minus 2 t magnitude square dt, which is going to be equal what? Integral from minus infinity to infinity. 100, 10 squared is 100, and then e minus 4 t magnitude, okay? So then here t magnitude means what? It means like we have a symmetric in both sides, so then we multiply by 2, and we can make the integral from 0 to what? From 0 to infinity, and 100 e minus 4 of t dt. Okay, 100 is constant, had nothing to do with integration, so then we'll get 200 and e minus 4 of t for the exponential divided by what? Minus 4, and we calculate the integral from 0 to infinity. Okay, so if we do that, we'll get what? We'll get 200 times what? Times 0 minus 1 over what? Over minus 4. Okay, so if we do that, we will get what? We'll get 50 joule. So then in this case, we calculate what is the energy dissipated in 1 ohm resistor by using the time domain. So then we know what is I of t. So just take I t squared, right? D of t integral from minus to infinity. So since we're talking about the magnitude, so then we can do the integral from what? From 0 to infinity, but multiply by 2. 10 become 10 squared become 100. And e minus 2t will become e minus 4t dt. So then the integration will be e minus 4 of t over minus 4 multiplied by 200. So then e minus infinity 0, e minus 0 is equal 1 over minus 4, we'll get 50 joule. Any question so far? Any question? Is it clear to everybody? Is it clear to everybody?
It's fine, yes, it's clear.
Okay, good. So Now let's try to find out how we can find the energy and the frequency domain. Finding the energy and frequency domain, we're using what? We're using Parseval theorem in this case. Okay. So then again, the first step we have to find out what? We need to find out what is I of omega. We know I of t is equal what? Is equal 10 e minus 2 t magnitude. So by using the Fourier transform table, we can find I omega is equal what? 40 over 4 plus omega square. Okay, so this is my I omega in this case. So since I know I omega now, okay, which is the Fourier transform for I of t, I can apply the Parseval theorem to find the energy. So W of 1 ohm is equal what? 1 over 2 pi integral from minus infinity to infinity. Okay, I omega magnitude square d omega, which is going to be equal 1 over 2 pi integral from minus infinity to infinity. I omega magnitude square, which is going to be 1,600, right? Over 4 plus omega square, everything is square, d omega. Okay. So if we look here at I omega is an even function, right? Since it's an even function, so can I just multiply by 2 and we'll conduct the integral only from 0 to infinity, okay? 1,600 over 4 plus omega square d omega, okay? 2 will cancel out. So then 1,600 will be out because a constant. So we'll get what? 1,600 over pi, and then we will use we'll use a table for that because not like an easy integral. So if using a table, we'll get what? 1 over 8 omega over omega square plus 4 plus 1/2 tan inverse omega over 2. So this is using a table, okay? Using integral table from 0 to infinity, okay? So if you do that, you will get, again, you will get 50 joule. So, but from here, I can tell that, finding the energy using the Parseval theorem is very complicated compared to the time domain. So if we need just only to find the energy, it's easier to use the time domain compared to the frequency domain for certain function. So why? Because you have to do, yes.
In short, you use the time domain instead of the frequency domain if you have a choice.
Yeah, if you have a choice, but
easier.
if you need to find the essential bandwidth to send a certain signal, so you must using the frequency domain. Okay.
Okay.
So if you know the energy of the signal, so you don't need to use the time domain. But normally we use the time domain to find the energy of the signal. And then we can use the energy of the signal and substitute that in a frequency domain to find out what is the required bandwidth. Okay?
Okay.
Because this is like in general, right? So again, if we look at the process is complicated and the integral will be more complicated compared to what? Compared to the time domain. Okay? Is it clear? Is it clear?
Yeah, that makes sense. Thank you.
Okay. So as a concept is clear, but maybe the difficulty might will be on conducting the integral, okay? So let's do an example here. For example, assume having a 1 ohm resistor, okay? So, and the current passing through this resistor, I of t, is equal E minus t, U of t, okay? Now the question here, we need what? What percentage of the total energy in the frequency band omega greater than -4, less than 4 radians per second. So we need to find out how amount of energy we have within this band, okay? So if we know what is the energy of the signal, so then we have to use here what? We have to use Parseval theorem to find out the amount of energy exists within this band, okay? So anybody tell me what's first we have to do? We have to find out what first?
You need to find the total energy so you can compare it to the energy in that band, right?
Right. So we need to find the energy using what? We can find energy using the time domain, right? So we need to find the energy using the time domain. So finding the energy, or we can use frequency domain here as well, you know. So we know one I of omega, since we're having I of t is equal what? E minus t, u of t, okay? So then in this case, I of omega is going to be equal what? 1 over 1 plus j omega. So everybody know that, right? So this from Fourier transform table. So then first step here, we need to find out what is I omega magnitude. I omega magnitude simply is equal what? 1 over square root, it's a complex number, 1 plus omega square. Okay? So then from here, I omega magnitude square is going to be equal what? 1 over 1 plus omega square. So we know what is I omega square, which is 1 over 1 plus omega square. Okay? So the next step here, we need to find out the total energy within, you know, if we do like W total, okay, is equal to, so if I need to sketch what's I omega is going to be, I omega is going to be something like that. This is my I omega. Okay, this is my I omega. And this is minus infinity to infinity. If we consider from minus infinity to infinity, we'll have what? We'll have the total energy. But in this question, we asked to find the energy from what? Within this band. This is minus 4 up to what? Up to 4. So we need to find the energy in this region. So finding the energy in this region, we see W total is equal what? 1 over 2 pi, right? Integral from minus 4 to 4, right? 1 over 1 plus omega square d omega. Okay? But now we know this is like a symmetric, so we can do the integral from 0 to 4 by multiplying by 2. So then 2 over 2 pi is equal integral from 0 to 4, 1 over 1 plus omega square d omega. Right? So then if we do that, we'll get what? 1 over pi integral from 0 to 4, 1 over 1 plus omega square d omega. Right? So then we know this integral is what? Is a tan inverse. So then we will get what? 1 over pi. So if we do the integral, so let's see here. 2 over 1 pi. Okay, here the total energy dissipated by the 2 ohm resistor is. Since we're talking about 2 ohm resistors, so we multiply here by what? Multiplying by 2. Okay? So the 2 here come from the resistor, 2 ohm resistors. So then 2 over pi, and then tan inverse of what? From 0 to, okay. So tan inverse W total energy. Okay, let's see. Okay. Yeah, this is fine. So then, yeah, this is, should be from where to where? From, okay, I think here, let's go back. Why is not using from 0 to 4? Okay. First we need to find the energy, but then we can find the energy, I think maybe using also the time domain. So here trying to find the total energy, okay, from minus infinity to infinity. And then we need to find out within this region from minus 4 to 4, okay? So because here, if we look at the equations here, we don't know what is W total, right? So we need to find out W total. One way to find W total, finding the energy, he's using here the frequency domain. But still, we will be able to using what? We'll be able to use the time domain, okay? How are we going to use the time domain? So if we do, okay, just keep this one for a moment, okay? So if we use the time domain, so we're going to get to the energy is equal integral from minus infinity to infinity, I square of t dt, okay? So which is going to be integral from minus infinity to infinity, right? I square of t, which is going to be, since we're talking from multiply by ut, so then we're gonna get what? E minus T square U of T square, whatever, it's gonna be the same, okay, dt, which is going to be integral from 0 to infinity, E minus 2T dt, okay? So we're going to use this one to find out what? Find the energy in time domain, okay? So then if we continue here, so then we have what? Integral from 0 to infinity, E minus 2T dt, which is going to be what? E minus 2T over what? Over minus 2, integral from 0 to infinity. So if we do that, we will get what? We'll get 1/2, okay? 1/2 joule, okay? So 1/2 joule here saying that, you know, the resistor is what? The resistor is 1 ohm. But if we're saying the resistor is 2 ohm, we just simply, I'm not sure why he's using 2 ohm later on, but let's assume 1 ohm. So then the energy is going to be what? 1/2 joule. So the amount of energy here for E of T is going to be what? It's going to be 1/2 joule. Is it clear? Is it clear how we find the energy?
Yeah, that makes
Time
sense.
domain?
So
Yes.
why did the time domain energy turn out to be half of the frequency domain energy?
It is not, because I think in the question here he using like 2 ohm resistor. I'm not sure why he's using 2 ohm resistor. Okay? So if
So he's saying 2 ohms dissipates more energy than 1 ohm? Does that make sense?
yes.
Okay.
Yeah, I square R, right? I square times R, right? This is the energy, right? So then here he assuming here like 2 ohm. That's why his 2 is coming from. So if you don't have 2 here, you're gonna get what? You're gonna get 1/2 joule. So then it is much easier to use the time domain, finding the energy rather than the frequency domain. If to be consistent with the solution here, we just multiply by 2 here. If we multiply everywhere by 2, okay? Since we're talking about like 2 ohm resistor, so then we will get what? We will get 1 joule in this case, okay? So assume the resistor here is like, rather than 1 ohm resistor is like 2 ohm resistor. So then we'll get 1 joule in this case, okay? Because we're using the power dissipated, right? I squared times R, right? So then R2 is going to be what? 2I squared in this case. Is it clear to everybody? Is it clear? Is it clear why we have here 1 joule? We have 1 joule because mainly what we do here, we're using like 2 ohm resistors, okay? Because if you get back to the definition of the work done, it's the definition of work
Talking about a
done.
1 ohm resistor, and instead they
yes.
did the 2 ohm
Right.
resistor. It's just
That's
a mistake
true.
in the slide. It's not a big deal. I understand,
Yes.
sir.
Yeah, so the work done is equal to integral from maximum to infinity, P of T dt, which is P of T here is what? I T square R. So R is 2 ohm resistor, so then we're getting 1 joule in this case, okay? So now again, it's easier to find out the energy using the time domain rather than using the frequency domain, okay? So we use here in this slide how to find the energy in the frequency domain. So time domain is easier. Now we know what is the frequency, what is the energy of the signal, which is 1 joule. So we go back here again. Let's do it again. So then, if we go to the energy in the frequency domain, W is equal 1 over 2 pi integral from minus infinity to infinity, right? 1 over 1 plus omega square I omega. Let's write the formula first. I omega magnitude square d omega. Now we know what is this side. What is the energy? Anybody? What the energy can be here in this case? What is the energy? It's going to be 1 joule in this case, right? The energy is going to be in this case 1 joule, right? Right? So if I need to find out what is W here, W here is equal what? 2 times 1 over 2 pi, 2 is the resistor value, okay? Integral from minus 4 to 4, I omega magnitude square d omega, okay? So then, but here again, this is like 1 joule if we consider it from minus infinity to infinity. But here we're not considering from minus infinity to infinity. We'll consider just only within the band from minus 4 to 4. Okay. So then this will be equal 1 over pi integral from -4 to 4 I omega magnitude square, which is going to be 1 over 1 plus omega square d omega. Okay, why is that? Because I omega magnitude is equal 1 over square root 1 plus omega square. Okay, so rather than do the integration from -4 to 4, we can multiply by 2. So then we have what? 2 over pi integral from 0 what? To 4, 1 over 1 plus omega square d omega. Okay? So then this is going to be for what? 2 over pi, 1 integral from over omega 1 plus omega square is only tan inverse of what? Of omega over 1, right? And then the integral from 0 to 4. Okay? So this will be equal what? This is going to be equal 2 over pi multiplied by tan inverse of 4 minus 0, which is going to be 0.844 joule. See? We're almost having what? 48.4% within this region. Okay? So then the energy within this region, the percentage is going to be what? W over W total. Okay? So W here is going to be what? 0.844 over W total is 1 times 100%. So if you do that, you will get what? 84.4% of the energy presented within this region, from -4 to 4. In this region, we have what? We have 84.4% of the total energy. Is it clear? Is it clear to everybody?
It's clear. Can you, I know we went over this, but I'm still a little confused. Is this example, the numbers that we ended up with 0.84 joules and 1 joule, is that assuming a 1 ohm resistor or a 2 ohm resistor?
This is like 2 ohm resistor, not 1 ohm resistor. Okay? So just, to avoid confusion, just change in examples here a 2 ohm resistor instead of 1 ohm resistor. Okay? Just change in the slide, instead of 1 ohm resistor, this is like, it should be like 2 ohm resistors. Okay? So this is like 2 ohm resistor instead of 1 ohm resistor. Okay? Is it clear now?
Yes, sir. Thank you.
Is it clear? So yeah, so in this case, PT is going to be equal what? If you need to calculate P of T, okay? P of T is equal what? Equal IT square, right? IT square times R, which is in our examples here, it's going to be what? 2 IT square. T square, right? And from the definition of the energy, W is equal what? Integral of what? Of BT dt, right? BT dt. So this is my BT. Just substitute here. That's where we're getting what? The 2 from. So it's going to be 2 integral IT square dt if I need to find out the energy in time domain. Is it clear? So then we find out here it's very important to use Biot-Savart theorem to find the bandwidth, the essential bandwidth required to send the signal, because in some of the example, might will give you what? Might will give you the percentage, and we need to find out what is omega in this case. We can do the same thing here. If I know what is the energy, okay? So if I need, for example, I need 95% of the energy to be existing in this, find the bandwidth that contains 95% of the energy. Anybody tell me how we can do that? So this is my signal, right? So then what is given here, that this band from minus omega 1 to omega 1 contain 95% of the energy. So anybody tell me how we can find out omega 1 here? For the same signal. We're talking about the same signal here. We have 2 ohm resistor, okay? And then I of t is equal E minus t U of t. And we need to find mainly what is omega in this case. Anybody? Where we should start?
Okay, so we already have the antiderivative calculated, right?
Mhm.
So instead of having from -4 to 4, we would just do negative omega-1 to omega-1. And then instead of having a W, we would put 0.95.
Yes,
And then-
that's true.
We just solve for
Mhm.
the W1.
Okay, yeah, that's excellent. So we know here that the energy is what? W is equal 1 joule, right? So 95%. So the energy will be within this band is equal what? It's equal 0.95, right? This is the energy. So then 0.95 is equal what? 1 over 2 pi integral from what? From minus omega-1 to what? To omega-1, 1 over 1 plus omega square d omega, right? Which is going to be, again, here we should multiply by 2, right? With the 2 ohm resistor. So then 2 with 2 will cancel out. So then since the function is symmetric here, we can do what? 2 over pi integral from 0 to omega-1, 1 over 1 plus omega square d omega, right? And on the other side,
Wouldn't the 1 over 1 omega squared, wouldn't that whole fraction be squared?
no, this is like, because, no, not square, because,
You don't square the whole thing.
yeah, because I of omega magnitude is equal what? 1 over square root of 1 plus omega square, right? Right?
Oh, I see. Yeah,
Mhm.
that makes sense.
Yeah. Okay. So now what is unknown here? Only omega-1 is unknown here, right? So then 0.95 is equal to over pi, right? Tan inverse of what? Of omega-1, right? From 0 to omega, 0 to omega-1, right? Which is going to be equal what? 0.95 times pi over 2 is equal what? Tan inverse of omega-1. Okay? Right? So how we're going to solve it here? Solving this equations here, we just take tan inverse of both sides, right? So then if we do that, we'll get what? Tan inverse of 0.95 pi over 2 is equal what? Omega-1. Okay? Then we can find out what is omega-1. Is it clear? Is it clear?
Yes, sir.
So either we can find out what is the bandwidth, or mainly we can find out how much the percentage of energy we have within a certain bandwidth. Okay. So by that, I think we really covered thoroughly the Fourier transform. So I already posted long time ago, I think, some solved problem about Fourier transform, and there is some questions also within the notes. So your homework to solve at least 3 questions, okay? So you have to solve at least 3 questions. It's already, if you open like the file of solved problem, you will find some solved problem as well as some problem you have to solve. So solve at least 3 of them is going to be your coming homework, okay? Is it clear? And you have to submit that by, I would say, you have like 1 week from now, okay? So 1 week from now, you have to submit your homework. So regarding the midterm exam, your grade already posted in the D2L, as well as the homework, as well as quiz 1. Okay? So you can see your homework. You know, the result was good with curving, not without curving. But there is some few students that did excellent work. You know, so. But the other was not doing well. I think they should, you know, just try to work hard for the coming exam. And just for you, this is very important. So you're going to use this stuff all of your life, okay? So Fourier transform is very important. And even now in the coming chapter that we're going to go through today, again, we're going to use like Fourier transform, okay, as well. So whatever you miss, you're going to learn it again, okay? So do you have any questions before we move forward? Everybody's okay? Okay.
Yes, we're good.
Okay, very good. Okay, so
Hey,
in this
Dr.
chapter,
Cheyenne,
yes,
after class, would you please post this as a PDF? My computer can't view when you post it as PowerPoint,
okay.
and
I'll
I
do
can't print it out and take my notes. Thank you.
Okay, if you want, I can do it now. Let me see.
Thank you.
Okay, we can do it now. Okay, just give me like 1 minute here. I hopefully have PDF in the computer here. So I will do it very quick, even for everybody. So let's do that. Save as browse PDF. Okay, so we just convert that. So let's see. Desktop. Okay. Let me see if we can do that here. So then we have to go back here and then contents. Okay, so already there, okay? Okay. So let's go back to the class. In this chapter, we're going to talk about like analysis and transmission of the signal. So we're going to talk mainly about the channel. We're going to talk about filter, and when we consider the channel is causing distortion to your signal, and when the signal, we call it signal distortionless, okay? And we're going to use here definitely the Fourier transform as a tool for signal analysis in this chapter, okay? So I'm not seeing it. TY is advanced. What does that mean? Yeah, the homework is located again in the solve problem file. If you look at the solve problem file, you will see some homework problems that you have to do, okay? Okay. Some of the things we're going to talk about it here is the Fourier transform and its property. We're going to talk again about symmetric, constant time delay. It's very important. Frequency shifting and integration and differentiation. This is like the kind of some property of the Fourier transform we're going to use in this chapter. Okay. So we're going to talk about certain signals that were widely used in communication as well as in electrical engineering. We're going to talk about sine and cosine. We're going to talk about impulse and step function. We're going to talk about rect pulse, and we're going to talk about sync function. It's like kind of the signal that we're going to study in this chapter. And we're going to talk about the signal spectrum. Okay, and we'll talk about bandpass and passband filter, RS low pass filter, bandpass filter. We're going to talk about energy and power spectral density. We're going to talk about essential bandwidth. We just talk about it of the signal. We're going to talk about autocorrelation to obtain the power spectral density, and we'll talk about effect of filter on the signal as well. So why frequency domain? We talked about it before. One of the reasons why we use frequency domain because the Fourier series and exponential Fourier series are representing a line spectrum. It's not representing like a continuous spectrum. That's why we need to use frequency domain in order to get like a continuous spectrum. And most of the signal in reality has a continuous spectrum. So another reason signal pulse is random, noise, randomly modulated carrier, all of them have a continuous spectrum as well. And it's much easier to make a filter in frequency domain compared to time domain as well. And we have a lot of representation, good approximation for the signal. And finally, which is very important, so we can convert the convolution from the time domain to the frequency domain. So then we can find out what is the frequency response of the system. For example, we have done something in the exam. So if I'm having x of t is an input to what? Is an input to system which has the impulse response h of t, and we need to find out what is y of t here. If I need to find out what is h of omega, for example, which is the frequency response, which is very important in a lot of application. So one way to do that is to convert from the time domain to the frequency domain. So then x of t has become x of omega, and then h of t become what? H of omega. So this is my frequency response, okay? And then we're having y of omega. So h of omega can be what? Can be filter, can be anything, right? Can be integrator, can be anything. So then in order to find h of omega here, simply y of omega, the output, is going to be equal what? The input, x of omega, multiplied by h of omega. So if I know the relation between input and output, I can find out what is h of omega. We just simply divide both sides by x of omega. So then h of omega is equal what? Is equal y of omega over x of omega. So if I know what is my output, this is my output, and this is my input. And this is my frequency response, okay? So we can find the frequency response using the frequency domain, which is impossible to find that using the time domain, okay? One way to find the time domain is just find h of t, and then from finding h of t, you know, we can find, just take the Fourier transform, which is going to be very complicated. Why? Because y of t is equal what? Y of t is equal x of t convolution with what? With h of t, convolution with h of t. Okay? So then if x of t and h of t is known, we can find y of t. But if x of t is known and y of t is known, we cannot find out what is h of t in time domain. So we have to use the frequency domain in order to do that. So let's go back again to Fourier transform. So we know the Fourier transform of the signal can be found for signal. If I have a signal g of t and time domain, I need to find out the frequency domain of the signal of the Fourier transform. So g omega by definition is equal what? Integral from minus infinity to infinity, g of t e minus j omega t d of t. So if I know what is g of t, I can find out what is j omega. And on the other hand, if I know what is j omega, I can find out what is g of t by using the inverse Fourier transform. So I know what is j omega. So the difference here, g of t become what? J of omega e minus j omega t. Here we're using e j omega t, and instead of dt, we integrate with respect to what? To omega, in order to get what? In order to get g of t. Here's some example. We're going to do this again. So just to remind you, so if I need to find out what is the frequency domain for this signal, what's the Fourier transform? So this is like an exponential decaying function multiplied by 2. That means the definition is defined only from 0 to infinity. Okay, and then we need to find out what is the Fourier transform for e minus a t magnitude. So in this case, we have done this before. So f of t defined only from 0 to t in this case. So to find the Fourier transform, simply we're going to use the definition. So integral from 0 to infinity, y from 0 to infinity, because f of t is 0 in this area, this region, right? E minus a of t, the function of the signal, multiplied by e minus j omega t from the definition, d of t. So then we can add these two exponential, So then we're going to have integral from 0 to infinity, e minus alpha plus j omega t dt. So this is just an exponential function. It's going to equal e minus alpha plus j omega over minus a alpha plus j omega. And we evaluate the integral from 0 to infinity. Okay? So if we do that, we'll get what? 1 over alpha plus j omega. Okay? So 1 over alpha plus j omega, again, is a complex number, right? And any complex number has what? Has a magnitude and phase as well. Okay? So then f of omega for this signal is equal what? 1 over alpha plus j omega. So if I need to find the magnitude of f of omega, which is very important in many cases, is going to be equal what? 1 over square root of what? It's a complex number, alpha square plus omega square. Okay? Again, we can find also as well as that the phase of this signal. So the angle f of omega, and we have this before, but it's very important we do this again, is equal what? Tan inverse minus sine, because in the denominator, omega over alpha. So if we look at f of omega here, f of omega is what? Is an even function, but f of omega, which is the phase, is what? Is an odd function. So if I need to sketch the spectrum of f of omega, so simply f of omega would be something like that. This is my f of omega magnitude, okay, and defined from minus infinity to what? To infinity. So the spectrum here is what? Is a continuous. So I'm having a continuous spectrum in this case, right? And again, if I need to sketch the phase is going to be what? It's going to be an odd function, okay? So this is the phase of f of omega. So then I can find the signal in frequency domain, okay? So then again, this is omega, and this is minus omega, minus infinity to infinity in this case. But this is mainly the time domain. This is the signal in time domain. This is e minus a t, right? Minus alpha t. And this is f of t. And this is from 0 to infinity. So this is the time domain of the signal, and this will be the frequency domain. The frequency domain, we have what? We have the magnitude as well as what? The phase. Always, you're going to find the magnitude and the phase. As far as most of the cases, the signal will be what? Will be in the complex format. Okay? Is it clear? We have done this before. We just do like some kind of review here. So now, if we need to find out what is the Fourier transform for e minus alpha t. So that means t can be what? Can be negative and can be positive. So this side represents what? Exponential growth. So we have what? E alpha t, right? And from 0 to infinity, we're going to represent f of t is what? As exponentially decay. So we have what? E minus alpha t. So then here we have what? E minus alpha t. Exponentially decay, right? And here we have what? E to the power alpha t, right? Exponential growth. So then in this case, we're going to integrate from what? From minus infinity to 0, and from 0 to what? To infinity. Why? Because we have like two different functions here, mainly. So then we do the integral from minus infinity to 0, e alpha minus j omega t dt plus integral from 0 to infinity e minus alpha plus j omega t dt. Okay, so again, it's simple to find what this integral. So this e alpha minus j omega t over the angle, which is alpha minus j omega. Okay, integral from calculate from minus infinity to what? To 0 plus e minus alpha plus j omega t over minus alpha plus j omega. Again, we evaluate it from 0 to infinity. So if we do that, we'll get what? 1 over alpha minus j omega, right? First integral, which is similar to the previous one, right? It's going to be 1 over alpha minus j omega plus 1 over alpha plus j omega, right?
Dr. Taylor,
Yes.
those funny boxes on the slides, are those supposed to be like large brackets?
Yes. These boxes,
Yes.
yeah, just ignore them, you know, so that has nothing to do here. Yeah, you just make them boxes
Okay.
like this, okay?
All right, thank you.
Okay. So then, how we can calculate here 1 over alpha plus j omega plus 1 alpha plus j omega? Anybody? We just combine them, right? So this, what's the common factor here? The common factor is what? Alpha minus j omega times what? alpha plus j omega, right? So then this is mainly the common factor. So then what is missing here? What is missing here? Alpha plus j omega, right? Plus what is missing here? Alpha minus j omega, right? This will be canceled out. So then we have what? We have 2 alpha over what? Alpha minus j omega, and alpha plus j omega is the difference, between 2 complete square. So then this is going to simply equal what? Equal alpha squared plus omega squared. Is it clear? Is it clear? So then in this case, this is mainly what is f of omega. Okay. So it's going to be 2 alpha over alpha squared plus omega squared. Again, the function is what? The function is an even function, right? But here we have the magnitude, which is exactly the same, but the phase is what? We don't have phase here, right? Because here we don't have like a complex number here. So just mainly the magnitude here will be this exactly same as this one, 2 alpha over alpha squared plus omega squared. So if I know what is alpha, I can find out what is the Fourier transform for any function in this case. Okay, now let's talk about Fourier transform where again, from g of omega is equal to the Fourier transform of g of t, as well as g of t is equal the inverse Fourier transform of g omega. So then from g of t, I can get what? G of omega. Or from g of omega, I can get what? I can get g of t using the definition here. G of omega is equal integral from minus infinity to infinity. G of t e minus j omega t dt. And g of t is equal 1 over 2 pi integral from minus infinity to infinity j omega e j omega t d omega. So either if g of t is known, we can find g omega. If g omega is known, we can find out g of t. Okay. Again, it's very important here to plot the spectrum, especially when we're talking about like filter. So g omega is always a function of what? Function of omega, continuous function of omega. And normally, most of the cases, g omega is what? Is a complex number. So we know complex number has what? Has a magnitude and phase. So I can write g of omega as what? If g of omega is the Fourier transform of g of t, okay? Fourier transform of g of t. So then g of omega can be written as what? As magnitude of g omega, right? Multiplied by what? By e j theta g of omega. So this is the phase, right? And this is the magnitude. Okay, so we know we can find the magnitude and the phase. So g omega is the magnitude and theta g omega is the phase of g omega. So some of the properties that we have to mention here is like conjugate symmetric property. What does that mean? If g of t is a real signal, then j omega and g minus omega are what? Are complex. So then g of omega is equal integral from minus infinity to infinity, g of t e minus j omega t dt. Okay. But if we need to find out g minus omega, we just simply, we're going to change what? Instead of minus omega, it will be what? It will be ej omega t dt. What that means? That means g minus omega is exactly same as what? Exactly same as g conjugate of omega, right? If we take like the g conjugate of this function, so simply we need to change what? We need to change out the sign here. Instead of becoming minus, become what? Become plus. So then g of minus omega is going to be what? It's going to be g conjugate of omega. Therefore, g minus omega is equal what? G of omega. So then the magnitude of the function is what? Is an even function, right? And again, theta j minus omega is equal what? Minus theta j omega, which means that the phase is what? The phase is an odd function. So for any real signal, the amplitude spectrum is what? Is an even function. It's always the case. And the phase of the spectrum is always the, is going to be like odd function, okay? Let's find the Fourier transform of the signal. We did that, and find the magnitude as well as the phase of the signal, okay? So again, by definition, we did this before, integral from minus to infinity, e minus alpha t u of t e minus j omega t dt. We just done that, right? So we can find out, this is my j omega, 1 over A plus j omega. So to find the magnitude, it's going to be what? 1 over square root alpha square plus omega square, E minus j tan inverse omega over what? Over A. So the magnitude is going to be what? 1 over square root alpha square plus omega square. And theta is going to be what? It's going to be, or the phase that's minus tan inverse omega over A. So if we look at the second slide here, we can see like the plot of j omega as well as theta j omega. So this is mainly represent what? J of omega, which is an even function, right, is defined from minus infinity to what? To infinity. And if you look at this line here, this is representing what? It's representing the phase, which is theta j omega. Again, it's an odd function. And as at this point is what? Equal, and changing the phase from what? From pi over 2 to what? 2 minus pi over 2. So this is the phase. Again, the phase here is what? It's not linear. It's a nonlinear phase in this case. Okay. And again, it's you're gonna see a symmetric here, right? So that's mean this is an even function. So j omega is an even function, and the phase here is what? Is an odd function. If you have a MATLAB, try to plot this one using MATLAB. So by the way, do you have the remote access to the software on the lab?
We got the document on it, but honestly, I have not tried it yet.
Yeah, would you please try, Sir Jan, would you please try to do that and inform everybody if you still work on the lab or you're not? No. So please try doing that, and if you're having any difficulty, please let me know, okay? But there is a procedure you have to follow in order to access. You can access all the software, exist in lab 214 as well as 217, okay? So please try to do that and let me know, okay? So let's have a break for 10 minutes and we'll continue, okay? So we'll go back to 145, okay? We'll continue again at 145. So let's just have a break for 10, 12 minutes. Okay. Let's continue. Do you have any question before we continue? Do you have any question? Okay. Now let's talk about some special signal we use in communication as well as in electrical engineering field. The first function we talk about, which is we call a unit gate function. Unit gate function is defined as what? We call it again as a rect function, rect of x. So rect of x is defined from minus 1/2 to 1/2. This is mainly a rect function, okay? A rect function is also what? Is an even function, is a symmetric, defined from minus 1/2 to 1/2. This is x, and we call this function rect of x. Okay, and if we look at the one on the right hand side, is also again a rect function. Well, this rect function defined in time domain from minus tau over 2 to tau over 2. Okay, so then in this case, it's going to be what? Rect of x over tau. Very important. So defined from minus tau over 2 to tau over 2. So the function will be what? Rect x over tau. Defined from minus 1/2 to 1/2. So it's going to be what? Rect x over 1 mainly, which is going to be rect x. So rect x is only just what? Rectangular pulse with a unity unity of high 1. And the width as well is going to be what? As well is going to be 1. So why we're interested in that? Because if we look at the digital signal, the binary data stream is going to be what? It's going to be represented as what? As a rect function, right? So we need to find out sometimes what is the Fourier transform, so then we can identify what's the bandwidth required to send certain signal, okay? So to find the Fourier transform for this type of signal, so we can use a differential. First, direct x is defined from -1/2 to 1/2, so and the amplitude or the height is equal 1. If we take from -τ/2 to τ/2, this is going to be what? Direct x over tau in this case. Is it clear? Is it clear? Do you have any question about direct function?
Nope.
Okay, let's talk about how we can find the Fourier
I lost-
transform of this function.
Oh.
Yes.
I lost audio for a second, but I think you're about to explain. I thought maybe you had already told us how to get the Fourier transform.
Yes, we did that, but we're gonna work on this again because do you remember what's the Fourier transform for this function?
No.
It is a sinc function. Okay, it is a sinc function. Sinc function is like sine x over x, right? We define sinc function, sinc x, as sine x over x. Okay, so this can end up the Fourier transform of the gate or the direct function is what is a sinc function. Okay, let's do this again. Anyway, but another function that we use also is a unit triangular function. Again, a unit triangular function is triangular pulse of a unit height and a unit width. Okay, same thing here. And instead of having a rect, we're having what? Triangular function. Again, rather than using a rect, we use a delta. So then this is delta x, and define the amplitude is 1 in this case, okay, and from -1/2 to 1/2, okay, and then we need to define the delta function from -τ/2 to τ/2. So then we're gonna have what? Delta is equal x over tau. Okay, so we call this one again as triangular function. And do you remember how you found the Fourier transform for triangular function? Anybody? What we used to find the Fourier transform for triangular function? You remember? Okay, one way to do it, we can find out by using what? By using the definition of the Fourier transform, which is going to be very complicated to do that, right? Because we need to find the integral from -1/2 to 0. And this is like a linear function of t, right? Plus y-intercept. And then we're going to do the integral by what? By parts. And we have different function here. Again, using the definition, we have to do integral by parts. So one way to find out the Fourier transform for this function, if you remember, we use what? We use differentiation property, right? We take the derivative of this function. The first derivative will make it what? Will make it a square function, right? And if we take a second derivative, we'll make it what? We'll make it a delta function. So then it's easy to find out what's the Fourier transform of delta function. Please review your slide, and Fourier transform slide. So it's in detail. We found out, explained how we can find the Fourier transform for triangular function. Okay, just review your slide. Okay, so another function which is very important in signal processing, especially for filtering and interpolating, so is a sinc function. The good thing about the sinc function is what? It has a value equal 1 at the main lobe, okay? And it have like multiple zero crossing. For example, this is like the first zero crossing. This is going to be the second zero crossing, the third zero crossing, and the fourth zero crossing, etc. And as time goes to infinity, we're going to expect the function to be equal what? To be almost 0, right? Same thing here. We have a sinc function is an even function. Okay, so here we have like a positive zero crossing. Again, we have a negative zero crossing. So we have a zero crossing at pi. What that means? That means the sinc function at this point is equal 0. Same thing here at minus pi is equal to 0. If we continue here, again, at 2 pi, we have what? We have a zero crossing. So the sinc function, we can write sinc function is equal what? Sinc of x, we can write it as follow, right? Sinc of x is equal what? Is equal 0, right? When what? At plus or minus n pi, right? When this angle is not plus or minus n pi, the sinc function is equal 0. So from that, we can find out what? We can find the zero crossing of the sinc function. So this is like the main loop, okay? And this will be here the zero crossing here. But if you find out, if we look at the sinc function, we're having what we call the side loop, okay? This is we call it the side loop. And side loop is not good when we talk about what? When we talk about like digital communication application, because each rectangular pulse is going to be equivalent to what? To a sinc function in the frequency domain. So if you have a multiple pulse, so they're going to what? They're going to be overlap with each other. So when you do sampling in the frequency domain, what's going to happen? So you're going to collect information from what? From the side loop. And this is going to cause inter-symbol interference in this case. And we're going to talk about it in digital communication, how we can get rid of the side loop using, for example, equalization. Okay? So, yeah, side loop. Yeah, side loop. Yeah, side loop. Yeah. So this is like the main loop, not loop. Yeah, sorry, side loop. Okay, so this is mainly where most of the signal will be. So this is not good. It's undesired, especially when we talk about digital communication. If I'm sending a bit stream of data, so they will be overlap with each other. Okay, and one way to get rid of this side loop using equalizer. Okay? But this is how the sinc functions looks like. So it has a magnitude when x is equal 0. Okay, and it has a zero crossing with an integer number of pi, right? It's going to be like at n pi, 2 pi, 3 pi, and so on. Same thing here at minus pi, minus 2 pi, minus 3 pi, and so on. So it's an even function, and it has a zero crossing with a multiple of pi. Any question about the sinc function? Okay. So sinc function, as we said, is equal what? Sine x over x. So we know sine x. Sine x is what? That's how we're going to sketch a sine x, right? But here we're not having the sine x. We're having sine x, right? Multiply by what? 1 over x. So as x increase, so the value of sine x will be what? Will be decreased. When x goes to infinity, so then sine x over x is going to go to what? It's going to go to 0 in this case, okay? So sinc x is an even function of x, which is easy to tell from the graph. Sinc x is equal 0 when sinc x is equal 0 except only at what? At x equal 0, okay? So then this is very important here. So we can write sinc x equals 0 when x is equal what? As we said, as an integer number. So sinc x, why we use this formula? We use this formula to find the zero crossing of the sinc function, okay? So we have sinc x is equal to 0. What does that mean? That means x is going to be what? Plus or minus pi, right? Then plus or minus 2 pi, plus or minus 3 pi, etc. Okay? So these values, sinc function is equal what? Equal 0. So we use this one to find the zero crossing of the sinc function. So sinc function is what? Is a sinusoidal oscillated function, right? So it's keep decaying as x is what? As x increase in this case.
I got a question.
Yes.
Can x also be 0? For this state?
Yeah.
If
If
equals
x,
to 0 and
yeah,
plus minus
when,
5. Okay.
when x is 0, so then we're going to use what? If you remember from math, we use the L'Hopital's rule. So then we take the derivative and find when x goes to 0. So we're going to use this rule. Using this rules, we can find out that sinc of 0 is equal what? 1. That's why if you look at the graph here, it's equal 1 when x equals 0, except when x equals 0. But when x is an integer number, like pi, minus pi, pi, minus pi, minus 2 pi, 2 pi is going to be equal what? It's going to be equal 0. Is it clear?
Okay. Got it.
Clear.
Thank you.
Okay. So if we need to find out, for example, if I sketch sinc 3 omega over 7, if I need to sketch sinc 3 omega over 7. So then we know how to sketch the sinc function, but we need to find out what's the zero crossing for this function. Okay? So we're going to use this formula. Sinc x in general is equal what? Is equal 0 when x is equal what? Plus or minus pi, plus or minus 2 pi, and so on. We can use the same thing here. So this is the angle here, right? 3 omega over 7. We're going to get the first zero crossing at what? At plus or minus pi. Right? This is the first zero crossing. The second zero crossing will be what? When 3 omega over 7 is equal what? Plus or minus 2 pi. Okay? So the first zero crossing will be what? We can find out what is omega here from this equation here. So omega will be equal what? Plus or minus 7 pi over 3. So this is the first zero crossing. The second zero crossing, we just multiply by what? We just multiply by 2, right? So this is the first zero crossing. The second zero crossing, first zero crossing. So the second zero crossing will be what? We just multiply this one with what? With 2, right? So then it's going to be omega is equal plus or minus 14 pi over 3, etc. So the third zero crossing will be what? Will be 21 and so on. So if I need to sketch the sinc function in this case from the zero crossing, so then this is my function. Here we have what? This is the frequency domain, which is omega, right? And then we know when omega equals 0, this will be equal what? Will be equal 1, right? This point here is going to represent what? It's going to represent the first zero crossing. So this point will be 7 pi over what? Over 3. And then minus 7 pi over 3. Okay? So the second side lobe. Okay, somebody say I cannot see the whiteboard. Did you see the whiteboard now? Did you see the whiteboard? Okay. So the second zero crossing will be what? This is my second zero crossing, same as from the other side. This is my second zero crossing. This second zero crossing will be what? 14 pi over 3 and minus 14 pi over 3 and etc. Is it clear? Is it clear how we can sketch the sinc function? Is it clear to everybody? So this is how we can
It's
sketch.
clear. I want to see what Hannah says.
I think she has a problem with her camera, maybe, you know. So, but everybody can able to see the whiteboard, right? Right? Okay. So, do you have any questions how to sketch a sinc function? Is it clear? So everybody now knows how to sketch a sinc function. Okay. So this is mainly the sinc function. Okay. Now let's go back to, we need to find out the Fourier transform of the gate function, which is g of t is equal rect t over tau. So then, how are we going to find out the Fourier transform of this function? So we're going to use what? By definition, right? So this is my rect function. It's defined from minus tau over 2 to tau over 2. And here is 1, and this is rect of what? T over tau. It's time domain. Okay? Good. So, to find out the Fourier transform, so this rect function defined only from minus tau over 2 to tau over 2, and the amplitude is equal what? The amplitude is equal 1, right? So, by definition, g of omega is equal integral from minus infinity to infinity, rect t over tau, right? E minus j omega t dt.
Hannah says, please send her whiteboard so I can catch up.
Is this okay? this okay now? Okay, I'm limited with the camera also as well, so let's see. Just repeated what he on slides. Okay. Everybody's okay now? Okay. So this is mainly the definition here. So if we look at rect here defined only from where to where? From minus tau over 2 to tau over 2. Okay. So the first step here, we need to change what? The integration limit, which is from minus tau over 2 to tau over 2. So in this case, what will be the rect function? The rect function is only what? Is defined, which is equal 1, right? 1 multiplied by e minus j omega t dt. So now it's become a simple integral here, right? So we just need to find out the integral, so which is equal 1 over minus j omega, right? E minus j omega t, and the integral defined from where to where? From minus tau over 2 to tau over 2. Is it clear up to here? Is it clear? Okay. So which is going to be equal to what? Minus 1 over j omega. Then e minus j omega tau over 2 minus e j omega tau over 2. So then in this case, what we can use here? We can use the identity. So this is equivalent to what? To sine function multiplied by 2j. Okay. So if we use the sine function here, so we're going to end up with what? We're going to end up with, and multiply with, because you're having 2j here, right? So this is equal what? 2j sine what? Sine omega tau over 2. Okay. So this is what's the equivalent of the function between the two brackets. So we multiply this one with what? With 1 over j omega. So we have 2j sine omega tau over 2 over j omega. So j with j will what? Will cancel out. So then we will have what? 2 sine omega tau over 2 over omega. Is this sinc function? Still is not the sinc function. Why is not the sinc function? Sinc function should be sinc x over x. So here we're having what? The angle omega tau over 2, and here we're having what? Omega, right? So then what we should do here, we should multiply by what? The numerator and denominator with what? With tau over 2, right? So multiply with tau over 2. If we multiply numerator and denominator with tau over 2, let me take this one out here. If we multiply by omega tau over 2 over omega tau over 2, what we will get? We will get tau sine omega tau over 2 over omega tau over 2. So now we're having the same angle here. So then we can rewrite this one as what? As a sinc function. So then this will be equal, is going to be equal tau sinc omega tau over 2 over yes, over 2. So then the Fourier transform of rect function is what? Is a sinc function, sinc omega tau over 2. Is it clear? Is it clear to everybody? So the rect function here is going to be what? It's going to be a sinc function in the frequency domain. Okay, so the tau, the amplitude is going to be tau, the highest amplitude, and then it's going to be what? Sinc omega tau over 2. I'll give you 1 minute, or I'll give you like 3-4 minutes to plot tau sinc omega tau over 2. Would you please do that without looking at the slide? Try to plot tau sinc omega tau over 2. Okay, try to plot tau sync omega tau over 2. I'll give you 2-3 minutes and then we'll continue. Okay.
Tim,
Yes.
Hannah asked something about so you can upload recording, but I told her I think it's
I
should
think
be
it's
able to be-
already will be there, right?
I'm sorry.
I don't need to upload the recording. Already will be in D2L.
Okay, so it should be in detail as soon as we
Yeah,
end this
should be in
study
D2L.
session.
Yes.
All right, cool. Thank you.
Thank you. Okay. Let's do this together, okay? So we just find out that rect function, which defined from minus tau over 2 to tau over 2, is rect of x over tau is a sinc function. Tau sinc omega tau over 2. So what we need now to do to sketch sinc omega tau over 2. Okay. So then to sketch sinc omega tau over 2, we need to find out the zero crossing, right? Sinc omega tau over 2. So the first zero crossing is going to be what? When omega tau over 2 is equal what? Plus or minus bar, right? So from here, we can find out what is omega, which is going to be plus or minus 2 by over what? Over tau. So the second zero crossing, let's name it omega 2, it's going to be what? Plus or minus, you just multiply by 2. 4 by over tau, right? And omega 3 is going to be what? Plus or minus times 2 is going to be what? 8 by over tau, and etc. So now I know what is the zero crossing. I know we're going to have the magnitude. When omega equals 0, the magnitude will be what? Will be tau. So then I can sketch my sinc function in this case. So the sinc function will be as follows, right? So this is like the main lobe here, right? This is tau. The first zero crossing is going to be what? It's going to be 2 by over tau. And the other side, we have what? Minus 2 by over tau. Okay? So the second zero crossing will be what? You can do the second zero crossing, which is here, right? It's going to be at 4 by over tau and minus 4 by over tau, and etc. Until it reach what? Until it reach 0. So this is the time domain. Yes.
What W1, 2, and 3 are?
The first zero crossing, second zero crossing, third zero crossing, etc. Okay. So
Okay.
at W1 we have the first zero crossing, the second zero crossing, the third zero crossing, and etc. Okay. So this is the first zero crossing, second zero crossing, and the third zero crossing in this case. Okay. So this is like the time domain, and this is mainly the frequency domain. So the Fourier transform for a rect function is going to be what? It's going to be a sinc function. As I said, in practical, we're not sending only one rect function. We're sending what? We're sending a series of rect functions. So we're going to expect in the frequency domain overlapping between what? Between the main loop for the second pulse, right? With what? With the side loop. So in this case, when we do sampling at the receiver side, this is going to cause something called interference. Okay? So intersymbol interference. So to avoid intersymbol interference, we do what? We do like equalization, and we'll talk about it, you know, when you take like a digital communication system course. But now what you need to understand, a rect function is going to give you what? A sinc function in the frequency domain. If I ask you a question, what is like sinc function in time domain? What will give you?
A rectangular pulse.
So it's going to give you what? A rectangular pulse in what? In frequency domain, right? Based on what? Using what? There's property we can use. We're using what? We
The
use
conjugate
not conjugate.
symmetry.
We use what? Anybody knows? I'm going to give you like 1 point in your midterm exam. So what we use? We go
UL.
from rect, we go to sinc, and then from sinc to rect, right? Yep, that's true. Duality, yeah. Excellent. Okay. So you're gonna get like 1 point in your midterm exam. Yes, we're using duality in order to do that, right? So we rect, we can get what? We're getting sinc, and sinc, we're gonna get what? Rect. And if you remember the duality, just to remember that, if I'm having f of t, right? Thank you, Hannah. F of t, the Fourier transform for f of t is gonna be what? It's gonna be f of omega, right? Right? Now, if I interchange f of omega by what? By t. Change omega to t. Now we'll have another function, not f of t, it's another function, f of t. Okay, so if this is like, for example, rect, this is sinc of omega, this is going to be what? This is going to be sinc of t. So this function is not same as this function. They're different. This is rect and this is sinc. So based on duality, we can find out what? We can find the Fourier transform of this function, right? We can find, this is Fourier transform, right? We can find the Fourier transform of this function. Finding the Fourier transform of this function, I don't need to use the definition. We can use it simply by using what? What is the duality? Anybody? We just do 2 by multiply by what? F, small f, and we change t to what? 2 minus omega. So 2 by f minus omega will give you what? Will give you the Fourier transform for f of t. So this property, we call it what? We call it duality. So we have f of t, Fourier transform will get f of omega. So if we change omega to what? To t, so we'll get what? F of t. So then we're going to expect the Fourier transform for f of t is going to be what? It's going to be, again, 2 by f minus omega. So if we start with rect function, the Fourier transform for rect function is going to be what? Sinc function. But sinc here in the frequency domain. If I change omega to t, so then sinc function become in time domain. So to find the Fourier transform for this sinc function, we just use what? We just use the duality. So it's going to be 2 by f minus w. Is it clear? Is it clear to everybody? Is it clear? So duality is very important to find out the Fourier transform for function that is difficult to find it using a normal definition of the Fourier transform. Okay. So this is mainly how it looks like. This is the sinc function. Okay. This is the first zero crossing, second zero crossing, etc. And at 0, we're gonna have what? We'll have like the high value, which is equal to in this case. Okay. Now, other function we're interested in is an impulse function. Impulse function is very important because it's like the heart of sampling theorem is what? Is an impulse function. If we need my answer for everything, duality. Okay, so then if I need, so g of t is equal here as what? Is equal delta function, delta t. So the Fourier transform of delta t is equal integral from minus infinity to infinity, delta t e minus j omega t dt, which is equal 1. Anybody can explain why this is equal 1? Why this is equal 1? No, it's not duality. It's not duality. I'm going to take the point back, okay? I'll take it back. Why this is equal 1? Actually, we explained this before. Why integral from minus infinity to infinity, delta t e minus j omega t dt is equal 1. Okay, if I need to sketch e minus j omega t, it's going to be something like that, right? Right? This is e minus j omega t, right? Right? Yeah, it's the definition of delta, but if we need to find out why this is just going to be 1, because we need to multiply e minus j omega t multiplied by what? Multiplied by a delta function, right? Multiplied by a delta function, which is delta t only defined here, right? At this point, right? This is my delta function. If I multiply e minus j omega t with a delta function, so then how many value will get here? We're going to get only one value. So you multiply this function with 0, right? It's only we're going to have value here, right? Right here. And this value is going to be what? E minus j omega 0. Right? Where e minus j omega 0 is equal what? Is equal 1. That's why this integral is equal what? Is equal 1. Why? We're multiplying this one sample, the delta function, with what? With the function here. We're going to get value only at this value when t is equal 0 in this case. So e minus j omega 0 is equal what? Is going to equal 1. Is it clear? Is it clear? Because this is going to equal value only when e minus j omega 0, which is e minus j omega 0 is equal 1. So this integral will be equal 1. Okay? So that's mean for all the frequency, the Fourier transform for delta function is going to be what? It's going to be constant for all frequency. Okay? So clear? Okay. So find the inverse Fourier transform for delta omega minus omega 0. We need to find out the inverse Fourier transform for delta omega minus omega 0. Okay? So now it's the opposite here. So then inverse Fourier transform for delta omega minus omega 0 is equal what? 1 over 2 pi. Again, we're going to use the same thing here, right? So we need inverse Fourier transform of what? Of delta omega minus omega 0. So this is my function. This is, we use inverse Fourier transform 1 over 2 pi, right? Integral from minus infinity to infinity, right? Delta omega minus omega 0, right? Multiply by what? E j omega t d omega. Again, we can use the property of what? Of a delta function. What does mean here? I'm having e j omega t, okay? Which is assume exponential increase, whatever. Okay, so this is e j omega t, okay? And we need to multiply it with a delta function. This is my delta function. Delta function is defined only at what? At omega 0. Okay? So if you multiply this function with the delta function, we will get only one value here, right? Which is this value is going to be what? E j omega 0 t, right? E j omega 0 t. What that means? That means the value of this integral will be what? Will be only equal e j omega 0 t. Because only we can find value for this function only at what? At omega 0. So in this case, we will get what? Ej omega 0 t over 2 pi. This will be equal what? Inverse Fourier transform for delta omega minus omega 0. Okay. The importance of that, we can find out what is the Fourier transform for Ej omega 0 t is equal what? 2 pi delta omega minus omega 0. And this is very important, and one of the where we did use that, anybody? We used this before. So we used this formula before. Ej omega 0 is equal 2 pi delta omega minus omega 0. Okay? We use this in what? Now, this is not like a phase shift. We just like multiply this like the delta property function here. Like, it's not like a phase shift. It's similar to phase shift, but it's not a phase shift, okay? So we just multiply delta omega minus omega 0 with this function. So we're going to get value only at this point, okay? Aj omega 0 t. So, but this is like a very important thing here. Ej omega 0 t is equal to 2 pi delta omega minus omega 0. So we can use this one to find out what? To find out the Fourier transform for cosine and sine function. It's like one of the things where we use this formula here, because sine or cosine can be written as what? In terms of exponential function. So, for example, if we have a cosine omega t here, cosine omega t here is equal what? I need to find the Fourier transform of cosine omega 0 of t. So cosine omega 0 of t, we're going to use this formula, Aj omega 0 tau. The Fourier transform is equal to 2 pi delta omega minus omega 0. So we're going to use this property to find the Fourier transform for cosine omega 0 t. Cosine omega 0 2 is equal what? Is equal 1/2 Ej omega 0 t plus E minus j omega 0 t. Okay? So then we need to find the Fourier transform of both sides. So Fourier transform of cosine omega 0 t is equal 1/2 Fourier transform of Ej omega 0 t plus 1/2 Fourier transform of E minus j omega 0 t. Okay? So then we can use this property here to find out what is the Fourier transform of Ej omega 0 t, which is going to be equal what? 1/2 multiplied by 2 pi delta omega minus omega 0 plus 1/2 times 2 pi delta omega plus omega 0. Okay? So then 2 will cancel, right? So then we're going to end up by delta omega plus omega 0 plus delta omega minus omega 0. What does mean here? If I take the Fourier transform of a cosine function, I'm going to end up with what? With two peaks, one peak at omega 0 and another peak at minus omega 0. So then the Fourier transform is going to be something similar to that. So we're going to have a peak at what? At minus omega 0. And then we're going to have another peak at what? At omega 0. So this is the two peaks which you have seen when we study when you see like the peaks of amplitude modulation. You have one at the carrier with the upper sideband and lower sideband exactly the same. So mainly we do what? We do a Fourier transform. A Fourier transform implemented by using FFT, fast Fourier transform. Okay? So this is going to be like, this is omega and this is minus omega. Okay, so then again, this is a continuous function. If you see only in the slide, you're going to see like only delta function at omega 0 and minus omega 0. If you look at the delta function by itself, it looks like as a discrete function, but in reality, it's a continuous function. So in reality, that's how it's going to be looks like. Okay, so then even if you see your sketch and find the spectrum for a signal, you're not going to see like 0. You're going to see like some values here. But only the peaks will be what? At omega 0 and minus omega 0. Okay? Is it clear? Is it clear? Do you have any question?
This is clear.
Okay. So if we multiply cosine omega 0 t with f of t, what's going to happen? Anybody? If I multiply cosine omega t with f of t. What will be the Fourier transform? And multiply f of t with cosine omega 0 t. What will be the Fourier transform? So we have f of t, and we multiply f of t with what? With cosine omega 0 t. So then the output here will be, the multiple will be f of t multiplied by cosine omega 0 t. Okay? So then what will be the Fourier transform of f of t cosine omega 0 t? Anybody? This one, Fourier transform of what? F of t cosine omega 0 t. What will be the Fourier transform of f of t cosine omega 0 t? Anybody? So what's this operation here? If you multiply f of t with cosine omega 0 t, what's going to happen for f of t? It's going to be shifted. You have done this in the lab, right? This is a simple AM modulation, right? This is an AM modulation, simple AM modulation. You multiply the message with what? With the carrier, right? So we're going to expect we have what? 1/2, right? F of omega plus omega 0 plus 1/2, let's make it common, f of omega minus omega 0. So what's going to happen for f here? It's just going to be shifted, okay? So this is mainly what, if we multiply f of t with a cosine function, what's going to happen is going to be scaled by 1/2, by a certain number, and it's going to be shifted by the same amount of frequency of omega 0. So f of omega plus omega 0 and f of omega minus omega 0. Okay? So if let's see, if f of omega here was at 0 and cosine omega 0 is like 200 kilohertz, if we talk about frequency, not about omega 0. So this signal will be shifted by what? By 200 kilohertz, and will be scaled by what? By 1/2. If this is 1, it's become the amplitude is what? 1/2. And it will be okay. I think let's stop here and we'll continue next time. But do you have any questions before we end the meeting? You have any question?
No, I appreciate you helping us out with all
Okay.
these
Well,
stuff you did today.
yeah, please.
And we did need some more time on the LabVIEW lab that you assigned last class period, and I haven't seen any kind of like format or formal.
You don't need,
outline
you don't
for
need,
it.
you don't need to do format here. We just need to do like to implement this one like LabVIEW and just send me the LabVIEW file. Okay, that's what you have to do.
Okay.
Okay, just do the LabVIEW file and send it to me. And we try to find out if we can do something remotely, because we receive like a 3-month trial from the company that they do Emona. So we need to find out if we can do some experiment remotely. We'll discuss that on Thursday, okay?
Okay.
Well, if you don't have any question, well, have a good day. Please be
Looks like
safe and
Hannah
take
had
care
a
of yourself.
Sir,
So what?
Hannah said, do you want us to email that submission to you, or put it in D2, or are you gonna have a folder for that?
Yeah, you can email it to me, or I can create the file. I will, just email it to me. Yep, email to me is fine as well. Okay.
And when do you want that by, sir?
By next Thursday.
By next Thursday. Okay.
Yeah.
Next Thursday should be fine, hopefully.
Okay. Okay. So please try
Should we make
to
it enough
access
time?
the lab remotely. Try to do that, and please let me know. And
Okay.
if anybody did it, just like share with others like your experience. Okay. Well, again, have a good day, and please take care, and we'll see you on Thursday. Okay.
Thank you so much.
Thank you.
And we'll see you.
Thank you.
Take care of
Bye-bye.
yourself.
Bye-bye.
Thank you. Have a good day.
You too. Bye. Take care. Bye.